Okay, the gold color one is a puzzle. You all like puzzles, right? Alkene puzzle. It comes with a riddle. This is from the Journal of Chemical Education. Number of alkene reactions. Each one you give a product. Well, there's a number listed with each one. Products are over here. And they have a letter associated with them. Then there's a riddle. How is the alkene able to learn all of its electrophilic reactions? The answer is because an blank, blank, blank. Each number of the reaction, you put in the corresponding letter for the answer. And you fill in the blanks to answer the riddle. Okay? This is a pretty good review. There are 3 reactions we're not covering, so I went ahead and gave you the letter. Okay? Those reactions, I covered those in Organic 2. We will not be covering them here. There is one mistake on it, unfortunately, typos are everywhere, right? We'll see this reagent, it should be 2 oxygens here. Okay. The other 2 handouts are on stereochemistry, which we'll be moving to as we move into next week. We got a good number of alkene reactions, though, still ahead of us. Okay, I sent out thermodynamic kinetics answer keys that were in your calculations. Hope you looked at that, ask any questions. I sent a video up top here. One of these reactions is very exothermic from your calculation. One of them is actually endothermic. The exothermic one, it turns out, also has a pretty low activation energy. Kind of makes sense because it's falling downhill. Usually when you fall downhill, it doesn't take much energy to give off that energy. There are exceptions like diamond. Diamond reacts with oxygen. It's very exothermic. But that has a high activation energy. It's hard to easily predict. Okay? One of those reactions is all it needs is like a little touch of a feather and it'll go. I sent you a video about that. You have to be careful when you're doing that type of thing, though. Anybody want to see the video? Yeah? Little explosive, exothermic. It's a reaction. This stuff here explodes, and what does it produce? This plus what? Heat or energy. Heat is a type of energy. Yes? Okay, there you go. That's that. We'll see what type of questions you have, if any. Intro to alkenes, nomenclature. Any questions about nomenclature so far? Easy terminology. Stereogenic alkenes. Okay, alkene reactions. That's our outline. Pink. We're looking at polymerization of alkenes. That's where we left off at. Yeah. Okay, cationic polymerization. If you take propene, react with H plus callus, you can get a polymer. Polymer is shown like that. Polymer is it's a monomer that's usually shown in the brackets. Okay? And this may just be shown. What's in the brackets? None of this may be shown. That right there is enough to know the structure. That is, it's a CH2 carbon methyl that just repeats over and over. CH2 carbon methyl, CH2 carbon methyl, CH2 carbon methyl. I just showed you how it's repeating. But all we have to do is just put that in parentheses with an N, which means some huge number. Like 100 gazillion. So you get this huge, long, single molecule called a polymer. Now polymers are a little bit ill-defined. And this, how long is this? We don't really know. What is the end out here? Well, that can vary. We're not going to look at all the details. If you want every little single detail, you take Chemistry 4960, Chemistry of Polymers. Okay? And first 5 minutes, you'll do this, and then the next full semester, you'll get the details. All right? We're going to look at mechanism for how you can get to that, understanding how you show a polymer in parentheses here, repeating units. Polymer chemistry is a huge and important field. Mostly, it's instead of looking at the atomic level, molecular level, you make things and you look at the bulk level. You know, I made this. What type of properties does this have? Well, it's hard. Polymer I made is hard versus maybe you make another polymer and it's softer or more moldable. So you look at more macroscopic properties. Now you can look at the molecular details. Again, that's advanced topics. Okay, mechanisms. It's our same old chemistry. H+. Alkenes react with H+, right? Where are we going to make cation? On the left, correct? And we get boom, 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 new H here, cation here. What can attack the carbocation? We're using an acid here that the conjugate base will not attack. You don't want it to attack. So we're using something like sulfuric acid or HF or phosphoric acid. We looked at those types of acids. You would not want to use HBr if you want to get a polymer, because Br would add here, and you'll just end up with this product, new H there. You don't want Br minus to add. What do we want to add to this cation?
Another propene.
Another propene. Can an alkene react with a cation? Yes, we did that above. We actually just did it here, except it was an H cation. Well, we can react with a carbon cation. Now when this reacts, it's going to leave cation here. Where? Top or bottom? On the top. So we pull away from the top, and we go bond here. What does that give? That's going to give boom, boom. Let's call the original so we can keep track. ABC. How about that? ABC, DEF for our carbons. Which carbon is now bonded to B?
F.
Or F. F is now bonded to B. All right? Our letters are going to be jumbled over here, but we know what they are here. That's boom, 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 boom. We'll keep the undrawn, we'll keep the initial H drawn in. I've got it drawn in there as well. What bond did we just make? 3 plus 3, 3 carbons plus 3 carbons is what?
6.
Very good. 6. 1, 2, 3, 4, 5, 6. Yes? Which bond did we just make? Right there, right? All right. This is D, E, F, and this is A, B, C. Where's the cation now? On which carbon? E. Yes, right here. Now what can attack? What can react with that cation?
Another propene.
Another one. Boom, boom. A, B, C, D, E, F, G, H, I. electrons here. That's going to give what? Boom, 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 boom. Now this is boom, boom, boom. And this is G, H, I, correct? I just bonded to E, right? Those have the same lettering. We just made this bond. Where's the cation now?
The top.
Right here. What can react with that cation?
Another one.
Please stop me whenever you want. Okay? What have we made here?
A polymer.
It can just keep on, we just did it 2 or 3 times. What if it reacted a gazillion times? Okay? What have we made? How can we show that? Well, let's look at it. We have this, in this case, it's just a hydrocarbon polymer. It looks like there was the initial H, but then from there it was what? CH2, C-methyl? CH2, C-methyl? CH2, C-methyl? And you keep going, so it's going to always be CH2, C-methyl. How can we show that? Well, it's a CH2, well, let's make this a CH2. We can draw it like this, and maybe cut it off here. Well, let's put the NH there. CH2, C-methyl, then what? CH2, C-methyl, and we could draw this nicely zigzag. Stop me when you want. It's the same thing as this, but it's just more cleaner looking structure. But instead of keep going, let's just somehow say that it just repeats, repeats, repeats. Well, what if we just take this and put the repeating part in parentheses, and that's kind of just going to something else that's not shown. CH2C-methyl, and this just repeats. And so we'll just put an N here. What I did, I had an N of 3. That's just because we stopped. I mean, we could stay here for a month and we could get an N of 100 gazillion. N can vary. So that's how you show your product there in parentheses. Repeating unit. Repeating unit has 3 carbons, just like your starting monomer did. Yes.
Isn't it a CH2CH methyl?
What did I say?
CH2C methyl? Isn't there a hydrogen on there?
There is a hydrogen, yes.
Okay.
There is an H there, yes. Okay, what type of polymerization is this? It's a cationic polymerization. What does that mean? It's initiated by a cation. What initiated this reaction? H plus catalyst. Is it really a catalyst? Well, it can be. See, I didn't finish it up out there. What's at the very end? I didn't show that. Again, very kind of ill-defined. Depending on how it ends, it may be a catalyst, it may be reformed, or it could actually not be. So I suspect that it doesn't have to be. If the H plus is consumed and not regenerated, you would not call it a catalyst. You call it a reactant or maybe a promoter, but it's certainly not a catalyst because that has a definition of that it's reformed at the end. It may or may not be reformed at the end. There are some that it does reform. Here's another way you can tell it's a catalyst. How much you add. For example, if you just add a very tracer amount, like a micro drop, and you get a huge amount of product, it must have been a catalyst. But if you add a micro drop and you only get a micro amount of polymer, then maybe it's because you didn't add enough H+. Well, we know if it's a catalyst, all you theoretically need is how many H+?
Technically one, right?
You only need one. And that's, can you just weigh out one molecule? One molecule you wouldn't be able to see. So a micro drop would be one molecule at least. If it's a catalyst, one micro drop is enough to create all you want because it just keeps regenerating. So that's one way to tell if it's a catalyst in practice. Okay, so there's polymers. Questions about that? If this was an anion that started the reaction, it would be an anionic polymerization. If this was a radical that started the reaction, it would be a radical polymerization. So polymer is a hugely important field.
Some of this is wood, maybe some woody material, but polymers all over the place.
That's plastic. Polymer. Plastics. Yeah? What's your favorite polymer? A thin polymer. Okay? Some polymers end up being more thin, and if you try to make them thick, they just kind of break or something. Where other ones are more easy to make thick. Because they have certain strength, and you have terminology for that strength, these macro properties. Okay, lucite. You ever heard of lucite? All right. Kevlar, you know? What is this? Looks like homework. THC. Ready with THC? Yeah? Bernard? Anybody? Here's a reaction. THC is formed in nature. Okay, there's lots of natural products. Plants out there are miraculous labs, miraculous chemistry going on in these trees and plants all over the place. Okay? Molecules like this being formed readily from CO2 and water and sunshine. All right. So this reaction takes place in the cannabis plant. What's going on here? This ring is being made. H+. Okay. This is catalyst. And you should be able to show a mechanism for that. Last time we did a ring-forming reaction up here at the top. Okay. This was an alkene attacking a carbocation, right? Well, in the THC example, it's some other type of nucleophile attacking the carbocation. So it's a very classical example of a mechanism. Anybody tried that one yet? Okay, pink sheet. What's next? B. What did it say, Alex?
Electrophilic conditions without
Without a carbocation. Everything we've done so far has had a carbocation intermediate. We can turn back and look at this here. We did these reactions at the top. Then we did a couple of miscellaneous things, reforming polymer, etc. These reactions involve a carbocation intermediate. Yes. Now we're going to be moving down below. And we'll be looking at these reactions here. Typical alkene. We'll start here, and we'll come around clockwise. This may look like a lot, but again, common consistencies. Really, what have we done so far? We reacted alkenes with H+, and then we had things attack the H+. We had things like rearrangements, potential for ring-forming polymer. That's about it. So you organize your material in a broad manner, and then you can apply that to anything. Same thing here. You'll have consistency. Just like in math. If you can do one math problem, then you can do 100 of them, 1,000 of them. There's no difference. Now, there will be differences here. You're going to have some different reagents, etc., obviously. But look for the common consistencies. That's where how you want to learn it, so you don't become overwhelmed. Just rely on memorization. Typically ain't going to work that well. Okay. First reaction is reacting alkene with X2. X typically halogen. This is like elemental halogen, like Br2 or Cl2. And we're back over here in the white. Okay. Called anti or trans addition of the halogen to alkenes. We take this alkene, react it with chlorine, Cl2. We can get a reaction, an addition reaction. Are they all addition reactions? Yes. The chapter heading, the handout heading, addition reactions. All these reactions are addition reactions, and they're all electrophilic, which should mean something to you. Maybe not quite yet, but you should know what electrophile is. Why is it called electrophilic additions? Okay? Headings are very important because it ensures that you're organizing your thoughts and you see what we're doing. My headings are very important. I would give you a heading that was just typing. Okay? I choose headings and everything very strategically. All right. Take this alkene. We can do an addition reaction, and we're adding 2 chlorines across the pi bond. 1 chlorine on each carbon. If you look at formula, this formula now has 2 chlorines added. Okay? Now there's no regioselectivity in this reaction. Previously we put an H here and a Br there, and then we said, well, could we do the opposite? Maybe we put a Br here and an H here. Does it matter where we put the chlorine? Chlorine's a chlorine. You put a chlorine on one, chlorine on the other, you're done. You don't even have to make that decision. So there's no regioselectivity to consider, right? See that? What's the mechanism for this reaction? Okay. Does Cl have a dipole? It does not have a permanent dipole. They have equal electronegativity. Okay? But your halogens, like Cl2, are known to be polarizable. They can readily take on a temporary dipole. Okay? Because the electrons are just easily perturbed. Okay? Various ways. Okay? And so it can easily become a temporary dipole. All right, chlorine, chlorine. Yes, we have a average non-dipole. But those chlorines are kind of doing all this all the time. Okay? And you pull, now I become positive. Okay? Very polarizable. Also, oxygen. Oxygen comes into the mix. And you bump up against these electrons. Whoa! Oxygen. Some other electrons can polarize the chlorine electrons. That's what it means to be very polarizable. Okay, that's what I'm doing here. And we can get to this point somehow. Now 1 chlorine is electrophilic. It likes electrons. These electrons move towards it. Well, these electrons move over here. Because chlorine can only have one bond. So electrons come in, kick the other chlorine off. Now you do not want to show this ionic. HCl we can show ionic because it is a lot of times. Cl2 never ionic. We have to work with it covalently. We come in here and make bonds, kick these off. 2 arrows there. What does this movement give? By the way, where are we going to make cation, left or right?
Left.
On the left. This swings out, makes bond to chlorine. We just made that bond. And what does this other arrow mean? The electrons are moving away from that chlorine, so the bond is being broken. It moves on to that one as the 4th lone pair. And that's a negative. At this point, the chlorine that got kicked off, these electrons could add here, and that would give that product, right? Please don't be concerned with how, if I do the chlorine up or down here. Okay? It looks like it's up here, it might should be up. That has free rotation, that's not chiral. Do you agree that the chlorine is now binding to this carbon right here? Yeah, chlorine's binding to that carbon. Doesn't matter how I draw it right now. A would give that product, right? That would be a mechanism for that, but it would not be the correct mechanism. The A pathway is not the correct mechanism. We know that. I'll tell you why on the next page. Instead of this happening, this chlorine attacks the cation. That makes sense though, right? Which one's closer to the cation?
The one already attached.
The one that's connected internally? Or the one that's way away? Internal. This makes sense. These electrons are going to hit here faster. I call that back bonding. These sort of back bond. Most books are not going to call it back bonding. I do. Some advanced books call it back bonding. And if B happens, what do you get? You actually get this 3-membered ring. If these electrons bond here. This is known to be an intermediate. We can tell you why, how that's known. Here the chlorine is positive, right? This is called a chloronium ion. It's a bridge 3-membered ring. Now, it's actually the only intermediate in this reaction. We'll talk about that. Let's finish it up first. From here, then that other chlorine or chloride comes in and attacks here. But here it kicks this chlorine off. Here we're starting to see leaving group. We attack an atom and the other one leaves, gets kicked off. We attack this carbon and this chlorine leaves this carbon. It gets kicked off. So we can call it a leaving group. Now guess what? Books won't call things leaving groups right now. They don't do that until later. But it's what it is. Okay. Why did we attack this chlorine? Because of a temporary dipole, it's partial plus, and electrons like positive. Why is this attacking this carbon?
There's extra electrons.
Because what?
Because there's extra electrons for it to attack the carbon
Extra electrons where?
on the Cl+.
Yeah, I mean, it's a nucleophile. It has electrons. But why that carbon? Why not the one on the end here?
Because that's where the carbocation is.
There's no carbocation. It's a neutral carbon.
It's because it has like a slightly positive charge because of the inductive effect.
Exactly.
Or-
You see some slight positive charge here, right? You got to see dipoles. right? That's a chlorine. Isn't there a dipole here? And that ain't just a regular chlorine, that's a positive chlorine. That chlorine's mad. Chlorine don't like being positive. That chlorine's like, give me some electrons, carbon. You might ask, well, why did you bond if you don't want to bond? Well, it does, because bonding's a good thing. It's a bond, but chlorine doesn't really like it. I'm showing it over here, okay? These electrons are being pulled. Sometimes books will show it like it's only a partial bond. If it's only a partial bond, that's a partial positive. But it can also pull over here, right? But it pulls more from this carbon. Why?
There's more stuff there.
Or I should ask this. More of the positive charge occurs here than it does over there. This carbon allows it to pull more. Why? Because this carbon has two rich friends. And so this carbon doesn't mind as much. Okay? You want to borrow money from me, chlorine? Go ahead, I've got rich friends helping me out, so you can take my money. This carbon over here is like, no, I'm not letting you take my money because I don't have rich friends. Okay? So you get more partial plus over here. That's what this is trying to show. Which is better? Would you rather have partial plus here or here? It's the same as if it was a full plus. You'd rather have a full plus there, right? Because it would be more carbon substitution. Well, the same idea as a partial plus. That's why we have more partial plus over here, and so this attacks here and not here. And if this attacks there and kicks off these electrons, what do you get then? Well, there you go. This is known to be the mechanism, not this simplistic attack. Okay? By the way, this is called backside attack of this. And as we'll see, if there's a leaving group on an atom, if we're kicking something off, the new group usually comes in backside. Backside could be more appropriately called opposite side. Okay? That'll be important when we do stereochemistry here. Okay, I drew this. This is not actually formed. That's not an intermediate. There's only one intermediate here. What's its name? That's right, chloronium ion. So why did I draw this if it's not an intermediate? I drew it to help you guys. I think it's more helpful to do it this way. But it's not actually formed in real life. Okay? In real life, these first two steps happen at the same exact time. Yes?
On the exam with the mechanism, like we have a mechanism question, if we write that, do we have to do NHF next to it? Or?
No, you have to do NAF.
Oh, so that was like.
It's an A.
Sorry.
Not actually formed. Not actually formed. Okay, here's how some books will do it. Bam, bam, bam. There you go. And there's your chloronium. Everybody see it? Good, let's move on. There you go.
So can we do that?
You can certainly do that because it's actually correct. But here's the problem with me. I don't think you're going to understand what you're doing. I try to present it in a way that I think is going to be more, you can understand as a very, it's the first time you've ever seen this. This is also useful because this guy, which is chloride or maybe a variety of other nucleophiles, is always going to attack here. And this is what I'll say. That's the same place that you would have had a cation, carbocation, if a carbocation had formed. It's the same outcome as if you had plus here. I mean, you could get the same. It's just it goes this way instead. But it's the same carbon. Which carbon do I attack? The same place we formed a cation. But it's back bonded. And we don't just attack a free cation. We attack and kick off that chlorine that had back bonded. Okay, you got to see this. If I just showed you this, could you have drawn the chloronium ion as a result of this here? Well, all this is combining the two steps. By the way, I hope Lopes would show you a lone pair there. What is this? This is attacking the chlorine. That's getting kicked off. Those two arrows lead to this. Then what happens? Then the chlorine that's bonded here, these electrons come in here and back bond. And it all happens at the same time. All this happens at the same time. Okay? You have a lone pair. You're a chlorine. Here's the alkene. And you're a bond. Make a bond, okay? Here we go. I attack you and knock your electrons off. Okay? All right, here we go. Boom. You leave now. These electrons coming in push you off. But at the same exact time, you got a back bond. Okay, here we go. Okay? You didn't back bond.
Okay,
Same
so-
exact time. In real life, it's the same exact time. Those two steps are the same exact time. Okay? You still ain't back bonding. As soon as I come this way, you got to be coming this way. Because as soon as I break away, this becomes positive. And your electrons, as soon as it becomes positive, you're attracted here. Boom! Chloronium ion, right here. Boom! Chloronium ion. This is never formed. I'm just showing you that on the board because I think it's helpful. Let's move ahead. Here's your mechanism. Predict the product. I think this is too much. All these arrows going up. All right? That's the way I do it. Probably nobody else does it that way. Just put NAF and you'll be good. Understand that it really ain't formed. That's just us on the board, on the paper, doing something to help us. Yeah? Taylor? Good? Show product here. All right, if we don't do stereochemistry and we don't do mechanism, but you should be thinking mechanistically, one of the easiest reactions is organic chemistry. Boom, boom, boom. Put a bromine on that carbon, and put a bromine on that carbon, and we're doing it. Those halogens add across pi bonds, halogen on each carbon. Right? You got to categorize your thinking here, okay? And that you could actually kind of memorize that a little bit. I mean, but then the mechanism requires more thinking and understanding. And then when we get to stereochemistry, you got to, right? Is that not the product? How about down here? Oh, what is ICL? It's just an interhalogen. Very similar. The difference is ICL has a permanent dipole. Which halogen is electrophilic here? Which halogen is electrophilic?
Iodine.
Iodine. Why'd you say chlorine?
I was thinking
Right. Because the chlorine is electronegative, it leaves a dipole like this, right? Making this partial positive and that's partial negative. In that situation, which one is going to like electrons more? As you learn in physics, electrons like positive. On the other hand, we can say positive likes electrons. The iodine is electrophilic as a result of the chlorine being electronegative. So which halogen does the alkene attack? Iodine, right? Because the electrons are going to attack the positive. Where are we going to leave cation at, top or bottom? Bottom. So we pull away here, attack the iodine, and kick these off. Alright? I got kind of... Attack the iodine, kick... What does that give? Boom, boom, boom. Iodine's bonded here. What's here? Cation.
And then iodine attacks that.
Well, let's ask a question here. Is this really formed? Or what can happen next? What's going to happen next, Joy?
The iodine attacks
Yes, these electrons, bam, going to back bond. What does that give? Iodine bonded here. That's a three-membered ring now. Charge of the iodine positive. That's called a correspondingly iodonium ion. Sometimes also referred to as a bridged, because this iodine is like a bridge between these two spots here. So let me ask you, do you think this is actually formed in the mechanism? Or as soon as this attacks, is the iodine going to be coming here? Yes, like we tried to. These electrons are coming in here at the exact same time. I'm just showing you two different steps. That's not actually formed. And here, going forward, anytime this over here has the new thing has a lone pair, it's going to back bond immediately. Okay? Concerted. Concerted meaning it happens at the same time. The first intermediate is right here. Plus Cl minus that we formed. Okay. This thing is strained. It wants to. It's going to react. Where's the chlorine going to add? Right or left? As I told you, it's the same answer as here. It's going to add right there. It's going to add right here. Why? Because this guy has a rich friend, and more positive can develop there. The product is this if it added here, but it adds this way. These electrons come in here, attack here, and we kick these electrons back off. The iodine gets them back. What does that give? Boom, boom, boom. Iodine here and chlorine here. And of course each, that's an I on the end here. Of course each halogen has 3 lone pairs. This reaction is regioselective. The iodine will be here and the chlorine there. We do not get product with iodine here and chlorine here. We do not get that product. The halogens bond to certain sites, certain regions, site-specific, regio-specific, regioselective. Because we know mechanism, we know polarity. Okay. How do we know it's this back bonding stuff and not just simple A? Wish I'd done something earlier, because prelude to this. On the next page, let's take a short 2-minute break. We're going to go back into back into this handout a little bit where we kind of skip something. Back over here, where on the side it said Stereochem. Need to look at that. Hopefully by Monday in that. Monday, Tuesday in that.
When are Tracy and Steve? Tuesday?
Literature?
Yes.
Monday, Tuesday.
In class or not?
That stuff is doing lab unless I tell you. Okay, guys, let's look back here where we did hydration of alkenes. Down here, predict products. Product was boom, 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 boom. That was the product, yeah? Everybody got that? Should be in your notes, yeah? Okay, guys, back here where we did hydration of alkenes. Okay, down here, this product should be this. What would be the stereochemistry of this product? Okay, 2 handouts I gave you today, we are looking at stereochemistry. Okay, that's the second major topic of test 2. We'll learn that we have chiral carbons. That's supposed to be a star. Chiral carbons. It's a tetrahedral carbon with 4 different things attached. Okay? We have different projections possible here. We'll be looking at that. Look at here though, that's a tetrahedral carbon. 2 in the plane, 1 forward, 1 back. But I've got 3 in the plane here. That's because I'm not really showing full details. I'm not showing the tetrahedral nature. If we kept the carbon skeleton in the plane, the OH we would need to draw either forward or back. We can draw it forward. We can also draw it back. And it has to be one of these ways. Or both. I mean, it has to be, it can't, it's tetrahedral. Its carbons are tetrahedral. Which one are we going to get here in this reaction? More importantly, what do we have to be thinking about to answer that? How did the oxygen become bonded there? Wasn't it a carbocation? What attacked the carbocation to eventually lead to this product?
Water.
Water, the oxygen of water. Okay. Well, the answer over here comes from how it attacks. We also need to know what's the geometry of this carbon right here. What's its hybridization geometry? Trigonal planar. Okay? Planar, like a piece of paper, or the board. Planar, flat. Flat surface. Okay? There's the cation. There it is, right there. It's planar. Okay? All right, it says plus on the other side too, because planes have two sides. Okay? Water attacks it. It attacks it from a side, a face. Okay? That is, here it is on the board. It either attacks here, and if it does attack from this side, the OH will be what projection at? Be forward, because it came from that way. Or it can attack from the other side. Now I don't have room, but what if the board was here? Then it could come here, and if it did there, it would be facing back, because that's the way it attacked. Okay? Which side is it going to attack from? Well, this is swimming around. Your water molecules, okay, you attack. Oh, you attack from that side, because you were over there. You attack from that side, because you were over there. So when you attack, you're going to be facing that way, and when you attack, you'll be facing this way. You get both. What's going to be the ratio? It's going to be about 50-50. If you know what sig figs mean, 50-50 is your answer. Now maybe it's 49.9999999% one and 50.0000. Because it's random. When you got a gazillion molecules and this is swimming around, half the waters are going to attack from one side and half the waters are going to attack from the other side. It's 50-50. Okay? You're going to get 50-50 of these. And by the way, we're going to call that racemic or racemic mixture. You get both of these. How do we know we get both? Because we know how to attack a planar carbocation. You don't just memorize that, you understand why. You attack a planar carbocation from either side. Okay? But some of you already know this because you've already read and been asking questions about the pink sheet. In the pink sheet, this is described. Two mechanisms for making nucleophiles to carbon bonds, which is what we do here. Nucleophile to carbon bonds. How do you do that? Two different ways. And I showed you this. If you add a nucleophile to a carbocation, you're going to get two different outcomes. Right? What is another way to add a nucleophile to a carbon? Kick off a leaving group. That is, kick something off. We're not attacking a carbocation here. Kick something off. Have we done that today already? Have we kicked anything off of a carbon? Yes, that was part of our chlorination, bromination mechanism. And that's it. Those are the two ways. It's hugely important for what we're going to be doing the rest of the semester. This is like taking math and me telling you how to add here. You've got to be able to add if you want to continue taking math courses. There you go, hugely important. This explains everything. Well, not everything. It explains everything we're about to talk about. It explains lots of stuff. Those two, understanding those mechanistic principles right there. It explains the stereochemistry. Now let's apply that back over here. How do we know it's not A and it involves this back bonding stuff? The reason we know is because if you do this reaction here with any alkene, this is an example, react it with chlorine, we add a chlorine to each carbon, but something very interesting. You only get trans. The chlorines are always trans. You never get a product from this reaction here where the chlorines are cis. We need to be able to rationalize that. Why only trans? Now, first off, we do understand cis and trans because this course builds. We introduce such cis trans. Well, now we're using it, okay? We're building upon that. Why only trans? Well, it comes from the mechanism. Basically, this mechanism does not involve a carbocation. The NAF, the carbocation is not actually formed. No carbocation. If there was a carbocation, this attacks carbocation, and then the chloride attacked it, how would it attack? From the front or back?
Either. Should it be either?
How would it attack the carbocation? Front or back? Both. Both, right? By the way, when this attacks and makes this bond, this is now tetrahedral. So this needs to be showed forward or back. Okay? Let's go this way. If I show that forward and this comes in, we can get two possible products. This should still be forward because nothing happens in the next step here. But then this is where this chloride comes in from the front, and that's where it comes in from the back. But look, if this was the mechanism, you would get both cis and trans. Right? But we know we don't get cis. This is not formed. So it cannot be that mechanism. Because we know if we attack the cation, it's going to be either side. Same way over here. If the first bond ended up dashed, and then this came in and attacked the cation, that would still be dashed, but this would be both up here. And again, this would give cis, but we know that that's not formed. So we need to modify our mechanism to account for this stereochemistry. The mechanism, and I don't have it drawn in here, wish I did, I got to draw it on the board. We know the mechanism instead is not that, but what? This back bonds, right? And when it back bonds, what do you get from that? I'll draw it over here. Well, this is still bolded. There's nothing happened here. But we have to draw it up a little bit to make this ring. Now this is bonded here. How is this going to be bonded? This is where the answer is not both.
Forward.
This has to be bolded as well. Why?
Because it's if it were flat, it's standing up, it's not gonna just magically go around to the back.
Here's the chloride, here's the cation. The chloride is already bonded, right? And it's sticking out forward. Here's the cation. Chlorine has to attack over here because it's positioned over here. Something else could attack from the back if it was free. Chlorine's not free, it's over here, so it's going to bond like this. Unless it's going to throw a boomerang, it can't do that. By the way, there's no way to have a, this is impossible to have. I can't have a three-membered ring. Here we go. 1, 2, 3. These have to be the same side if they're going to bond. If these are like this, they can't bond. It has to be. That's NaF. This is how it's formed. Now the chloride attacks here. And when it attacks here, we're going to push this off. Push these electrons off. And when you do that, how do you end up? You've already said it once. It was in that page that I showed you. Now, how do you attack? What's the terminology? How do you attack a carbon whenever you kick something off?
For backside.
Backside. Opposite is a little bit more clear, but it's called backside. I like opposite better. This bond's forward, so how's the new bond going to be?
Back.
Back. And this gives, I'm going to draw this over here, this gives this. We call this backside attack. And that chlorine will just be dashed. Anytime you kick the leaving group off, it's backside. Okay? Here we go. I got a hand with the leaving group. It's there. This thing's going to attack. It doesn't attack over here. It attacks here. It comes in here and kicks that off. And it's the opposite side now. Okay? Anytime you kick off the leaving group, it's... And so this chlorine is forward, right? Bolded. That comes in from the back, kicks that off. Now that's back. All right? Please look at the pink sheet mechanism. You can do the same thing over here, and that's an explanation for why you only get trans. Okay? So that's why we have to do this back bonding mechanism, because it's the right. We do not attack a free carbocation. Okay. Now moving forward, we have several other reactions to cover, but we will use the same principles. They'll just be new reagents, etc. Same core principles we just talked about. All right, if you do this reaction with a halogen but include water, you get a different product. You get halogen on one and OH on the other. This is called a halohydrin. Halo meaning halogen, Hydra, like hydration, because there's an OH on the other, like water was involved. Halohydrin. Now this reaction is going to be regioselective. In this example, the OH is going to be here on the tertiary carbon. We will not get a product with the OH on the primary carbon. Okay? So you do have regiochemistry here. But our mechanism would predict that. Okay, alkenes don't react with pure water, but they do react with chlorine. These electrons attack chlorine, these get kicked off. What does that give? Well, thus far on the board, it gives chlorine here, cation there. Yeah? Do you think this is really formed, or is something going to happen concertedly? Back bonding potential here. These electrons are going to back bond, I'm going to say NAF, and that's going to lead us to what?
Third ring.
Our chloronium ion. This is our first intermediate. Now what comes in and attacks this? Water in this case. Yes, you do have the Cl minus. Yes, it could attack. If you see water included in these reactions, water is what's going to attack. Why? Well, usually you use excess water, so there's just more water around. Water just is a better nucleophile here. It would have to take some good explanation. When you see water, you're going to use water. If you don't include water, Cl will attack here and you'll get the dichloride. Water attacks. It's your nucleophile. Which carbon is it going to attack? Because the chlorine is pulling on both.
The one with rich friends.
The one with rich friends. It allows more positive to develop there. And remember, the answer to that question is the same as here. You attack where the cation would be. We attack there. It's just we attack the back bonded thing. We don't attack a free cation. We attack here. And we kick these electrons off. What does that give? Boom, boom. I'm not going to deal with stereochemistry right here. I'm going to draw this a little more like this. And put the oxygen here. We don't magically lose an H. That leads to this intermediate. Then what's next? We have to go neutral.
Other Cl attacks the H.
What can take an H?
The
Cl.
flora.
This guy can take an H. These electrons stay behind. We form this plus what? HCl. Isn't it beautiful to be able to know that HCl is going to be formed here because we know mechanism and we see that? Yes, HCl is also formed there. You see it in the mechanism. What was different there from the previous reaction? The difference is water attacks instead of Cl minus. Again, I've got the OH drawn down. It's up here. Some of you know chirality a little bit. That's not chiral. It doesn't matter how you draw them. As long as it's connected, there it's fine. When we move forward, we'll clarify when it's important to draw it certain ways. It's not important. Do you understand now why the OH is up here and not out here? It's all from your mechanism.
Doesn't that one also have to be trans because the ring is formed?
What has to be trans?
The product?
Well, see, that's the case. The product doesn't have any cis-trans possibility. Because it's not, there's no chirality. Let's do an example where it does, though. Down here. Okay. If we did it here, and I'm just changing chlorine to bromine, same reaction. You're going to get this product. And the bromine and OH would be trans. Okay, how do you assess this reaction? With all your reactions, there's a little bit of memorization to get you going. For example, if alkene reacts with bromine and water, what type of products will we form? What type of product? This is something great for a note card. What type of product? Name of the product. Asia?
Halohydrin?
Halohydrin, yes. Alkenes react with halogen and water, make halohydrins. Boom, that's a little bit of memorization. Get you going, note cards. Okay? But then what's the intermediate in this reaction? The main intermediate. Now our mechanism there had two, but what's the named intermediate? Bromonium ion. Can we draw the bromonium ion? We could go through full mechanism. All right? It's going to be here. It's going to be this here. With a methyl, now the methyl's going to have to be going back. Because if that's forward, you've got to have one back. Now this is also plus enantiomer, and we'll talk about that going forward. The enantiomer would be where I drew both of these dashed and did that bolded. Okay? But if water attacks here, where's it going to attack? Top or bottom? Top. So water attacks here, kicks off bromine. What is that going to give? Now I'm going to eliminate the one step. I'm going to go to the product. This bromine will be forward. How will the OH be? Well, that's forward, so it comes in back. So this will be back. Here's a kicker you just have to accept. This pushes the methyl forward. Okay? That methyl is going to be forward. Okay, we'll talk more about that going forward. There's your product. And the OH and the bromine are what in my product? They're trans. Like I told you they would be. By the way, my example, this is the enantiomer. I said plus enantiomer. I ended up with the enantiomer here. That is the enantiomer. This stereochemistry is coming next day or two. But it's built in here. So I just put this is just in the notes for now. Okay? So terminology here, the bromine and OH have added across the pi bond, but they've added in a trans manner. We also call trans anti. That's why back up here it was called a trans halohydrin. But only if it's applicable. Here it was not applicable, so you don't really discuss the trans part. But when it is, you get trans. All right? Down here. Okay, you can predict products here. Do these on your own. We'll look back at them at some point.
Dr. Stevens,
Uh-huh.
so does that mean that top one isn't technically cis either? It can be anything?
Cis or trans is not applicable. It's like, is this female or male?
Okay, I see what you're saying.
Not applicable, not either. On the other hand, we could say, is this person female or male? We know that's applicable, because it's not applicable for that. Deuterium, you know what deuterium is? Yeah? Whenever you see deuterium in reactions, it's the same exact reaction as an H. The reason books and instructors like to use deuterium is because it allows us to differentiate between one H and another. That one gets called a D. And so it allows for some stereochemistry. But the chemistry is the exact same. Yes.
Can you explain why that was pushed over, like, why that was pushed up in the OH?
Why, what was?
Why was it moved to the forward position instead of staying with that?
Why the methyl got pushed forward? We're going to kick off the black pin. This comes in this way, okay? It comes in here and kicks it off, okay? But if this comes in here and just kicks off, that bond angle there is 30 degrees. When this comes in, this is going to move some like this and just occupy the space that got kicked off some. Okay, I don't have a third hand, but this comes in and kicks it off, and now it's bonded, but it just moves it. Because this vacated, so that kind of just moves this way.
So it just pushes it forward from behind.
Yeah, it just gets pushed. Because if it didn't get pushed, you'd have two things back. And now then you'd have an ugly, bad, terrible bond angle. So it just moves forward. Okay. Later on, we call that inversion. Okay, so there's some to work. Next reaction, epoxides. An epoxide is a three-membered ring with oxygen. Okay? These can be isolated. You may have heard of epoxy glues. Anybody ever worked with an epoxy glue? Okay. Because epoxides can then be polymerized and lead to things like glues. Epoxides can be made from alkenes using this here. This is condensed. This is structure shown here. If that was just one oxygen, OH, that would be a carboxylic acid. But it's got two oxygens, and so it's a peroxy acid. Okay? That's your main reactant. But one of the most common peroxy acids is where the R group is a benzene ring with a chlorine here. That's the meta position. Metachloroperoxybenzoic acid. Should be in your textbook. It's a common example. See, this is just generic, R group. So, a peroxy acid reacts with alkene to give epoxide. Mechanism. You got two oxygens like two bromines or something. But this one over here is bonded to the carbonyl. And this is pulling electrons this way. All this electron movement towards this oxygen leaves this as partial positive. And the alkene attacks that oxygen. Attack the oxygen, kick this leaving group off. That gives this plus the leaving group. Because the oxygen does have an H. You think this is actually formed? What could happen at the same exact time? The new thing has a lone pair. It can back bond. Okay? When it does, what does it lead to? This structure. Which is analogous to like a bromonium ion. The difference is this has an H. And if something takes the H, we can move the electrons onto the oxygen and we can go neutral. And you can actually isolate that product. And your leaving group acts as a base. Takes the H, electrons move here. And there you go. Hopefully you see the consistencies in the previous mechanism. We can make this. How many intermediates in this mechanism? One. One, right there, because that ain't actually formed. That's a nice little reaction, yeah? Using what type of reagent? Peroxy acid. Yeah. Yes. Okay. We can do some practice here. We'll do the first one real quick. I would do this recommendation. Anytime you're doing these reactions like this, just do it without considering any stereochemistry. Just connect things together right. Then if you're asked to, then go back and reevaluate and do it with stereochemistry. Anybody got the first product already? You got it, Ronan? I mean, if you don't consider stereochemistry, it's right up there with one of the easiest reactions organic chemistry, because all you do is what? You connect the two carbons with an oxygen. Did you recognize that that's all we did? There's your product. Yeah. Now going forward, you have one chiral carbon, and we'll have to learn how to deal with that potential stereochemistry going forward. Here you're going to have some stereochemistry that you can probably do now. Because once you have rings, you then have more defined stereochemistry and cis-trans possibilities. But again, first do it with no stereochemistry, then go back like this. I didn't consider any stereochemistry here. I just got it connected right. Then you can go back and consider what needs to be done. All right? Next reaction. We can react alkenes and make, what is this? What did we just make here? Also a three-membered ring, but here instead of adding an oxygen, we're adding this carbon. Two carbons, we're adding a carbon bridge. Not an oxygen or a bromine. And that's just a cyclopropane. And I mentioned before that a lot of cyclopropanes, a lot of drugs contain cyclopropanes, unusual large numbers. This can be accomplished using a reagent called diazomethane. Which would have been a good Lewis structure question. Can you draw a Lewis structure for that? Well, here you go. This is condensed, but it's carbon with two H's. Any way you draw it, you're going to have two charges. But it's net neutral. Okay? It's a neutral molecule. Turns out it's explosive and toxic. All right? We won't be using it in lab. And it's a gas, so it'll chase you around the room. You know, you spill a solid, it's going to lay there and you can sweep it up. The gases, okay, they're going to... If you heat this thing, if you heat it too high and too fast, it will explode and do this. But you can do it controllably. Here's the structure. With a little heat, this nitrogen will just leave. It's a positive nitrogen here. Would it like to take these electrons and just take them for itself? Yeah. And if we just move those over, what do we get? nitrogen gas, N2. What does it leave over here? It leaves this. It's a carbon with two H's. Have a lone pair. But when that leaves, what's now here? Nothing. That's it. That's this thing here. It's neutral. I mean, why am I showing a plus and a minus? Because, look, what's the charge here? How many electrons does it own?
3 or 6.
No, it owns one of these. It owns 4. How many is it supposed to own? 4. It's neutral. Neutral. This was on the test. What do you call such a carbon?
Carbene.
A carbene. Yeah. It's a divalent carbon that is neutral. Okay, remember on day 1 I said that if it ain't standard bonding, it should have a charge? Well, this ain't standard bonding for carbon. But it don't have a charge either, so it's an atypical carbon that is neutral. These can be formed. This is one way for them to be formed, from diazomethane. Just heating it, nitrogen will leave. Why am I showing 2 charges here? Because usually when carbon has a lone pair, it's usually minus. So it's got sort of minus character. And usually when carbon is missing the bond, it's usually plus. And so it's got that plus character. It has dual character, so I'm kind of reinforcing it by showing both charges. Okay? But it's net neutral. Okay. The alkene reacts with it. See, we can almost just consider it like a carbocation. And we can attack it and make bond, but it's got the lone pair left. Now it's a minus charge. And do you think this is going to back bond? Certainly it will. And when it back bonds, what do you get?
The product.
That's it. That's your product. From here, how many intermediates in the mechanism?
1. Or are we counting the first one as an intermediate or no?
In this,
Yeah.
we're just counting it as a reactant.
Then no.
There's no intermediate here. This reacts with this to get product. This reaction has sort of a pre-reaction, an activation step for something here. Usually when you're looking at reactions, say intermediate, you're talking about carbon-based intermediates. There's no carbon-based intermediate here. This is a carbene. But you know charges, okay? You know that's really net neutral. This is a true minus, that's a plus. Back bonds, you're done. You don't even have to remove a proton like we did with the epoxide. Pretty neat, yeah? Okay, that's just a standard cyclopropane. Not that convenient to make, although they can be. There's another example here where we make Dichloro Cyclopropanes. These are more convenient to make in the lab. That's another common introductory mechanism. Here you react the alkene with chloroform and hydroxide. Chloroform is actually often a common solvent. It used to be used as a anesthetic, sedate. Queen Victoria took chloroform when she gave birth, and that started a big trend of using chloroform for 50 years until better things were developed. Okay, there's a carbene formed. It's formed over here. Hydroxide acts as a base and takes the H. Chloroform has a little bit of acidity because the resulting anion is stabilized. How is it stabilized? 3 chlorines. If these were H's, hydroxide would not do this. Presence of the 3 chlorines pulling stabilizes the anion. Makes this acid base possible. At this point, this is actually a lot like diazomethane. One of the chlorines leaves. It just acts as a leaving group.
What's the reason for that?
Good question. Well, look here. Carbon's a minus. Does it like being minus? No, it's not that electronegative. But because of the chlorines there, it was able to do this. See, what happens here is this chlorine's like, okay, carbon, I know you don't like being minus. What if I just take the electrons and leave? Because I love being minus, right? Doesn't Cl like being minus? I'll become minus, and you can become neutral. Because that's really net neutral. The reason this leaves is because of the 2 atoms made a deal, and chlorine became minus. Chlorine gets what it wants, right? And carbon gets to go back towards neutral. I mean, this is how chemistry happens. Why, when sodium comes in the presence of chlorine, does sodium just give it the electron? Because chlorine loves electrons. And sodium would rather be positive, actually. See, atoms make deals, and that's chemistry.
Are there any other cases like that?
Any other what?
Cases like that?
Where atoms make deals?
Well, in that certain situation, so like, could it be 3 bromines instead of 3 chlorines, and bromine is the same thing? Or?
Yes, yeah. Yes, you can do this. Yeah. And that's an example of, we show one reaction, but you should be willing to say that then it can happen over here as well. You make connections. Because really what we're showing here is not just one reaction that we have to memorize and move on in. Okay? We're really learning basic principles here that we need to, that's the fundamental. So then we can take what we're learning here and apply it to this. There may be something over here. Yes.
So, I mean, should it be halogens then, or if it was another highly electronegative atom like oxygen, would that also happen? Or would it only be halogen?
No, that's a great question. You could then sort of semi-answer your question. Would oxygen be as likely to do that? No, because it's not as electronegative. Could it? I don't know. Maybe I'll try. I'll go to the research lab and try. Maybe someone else has tried it before and it doesn't work. But you take your knowledge and you apply it to new things. Okay? Once that leaves, chlorine's like, I'm minus now, okay? Well, now the carbon is like, well, yes, I'm neutral, but I don't have an octet. And by the way, that's the reason that this would attack that, because there's no octet here. And so now this guy comes in and is like, well, these electrons aren't held that tight. I can go bond with you and make a sigma bond. Now we got a stronger bond and everybody becomes happier. Well, now this lone pair is like, well, I'll go bond with you because I'm right next door. You see how everybody gets happier and happier? That's chemistry. Chemistry goes downhill and reactions take place. Is this actually formed? Would we expect it to be?
No.
No, you got a lone pair next door. As soon as this here is coming this way, guess what these electrons are doing? They're coming that way, and most books will show it at the same time. Again, I like to show these arrows separately. And I think it's better for you guys at the beginning. Just make sure you understand it. That's just Stevens on the board, you on your paper. Right? These are easier to make in lab because these are safer to use. That's a little toxic, but That's a liquid. Okay, more common in lab. Diazomethane's not that common. I've never used diazomethane. Okay. Again, just in terms of what the product is, let's see, an alkene, that looks odd. What is this? No card. That's diazomethane. What does it do? Oh, it generates carbene. Okay, this is a cyclopropane. Yes. Boop, 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 boop. And then between these two carbons is what? That's it. We're making a cyclopropane between the two alkene carbons.
What is pH? What is pH?
Phenol, which is a benzene ring. Stereochemistry, though. We have a ring here. Okay, again, drive without stereochemistry, then go back and assess. We should assess that, and we will learn more as we keep going. Eventually, you'll be able to go back and assess it. But we do have, that's a ring. And we have two things on the ring. Can you remember when we had two things on rings, we had cis or trans? You got that possibility here. Okay, there you go, other reactions to look at. You see the consistencies. Drugs with cyclopropanes. Okay, let's see where we're at here. Pink sheet, model alkene, X2, what do we get? Trans dihalide. We understand why the two halogens would be trans, we should. Typically with chlorine or bromine. This reaction here doesn't work with iodine, I2. Mainly because if you do the calculations, the reaction of an alkene with iodine is endothermic. Now you can do endothermic reactions. Problem is it's reversible. And since it's reversible, it goes back to starting. So it's not a good reaction. Now fluorine, on the other hand, F2, very exothermic because the CF bond is so much stronger. And F2, being so exothermic, it's dangerous to work with. If you add fluorine, it can just explode. Okay? Actually, there's a semi-joke, crude joke. How do you recognize fluorine chemists?
They're missing.
They're often missing fingers. Because they, okay? And I've known a chemist at Clemson who's a fluorine chemist, and he's missing a half an arm. All right? On one, and the other he's missing 2 fingers. Because in graduate school at a university like Washington in the 1960s, he was working with fluorine and there was an explosion. He's like 80-something years old now. Or 70s or whatever, you can do the math. Do what?
Is he missing a leg?
No, he's just missing what I told him. But he was a pretty well-known fluorine chemist, okay? So that's why we don't usually say F2. Chlorine and bromine are your 2 best. We'll actually use bromine in the lab. We'll bromine an alkene next week or very soon.
Wait, did he keep working with fluorine after that?
Yes.
We're
We're working for... See, I had lunch with him one day. I was lucky enough to have lunch with him, and back then they kept a tank of fluorine out in the the yard. You know, like a natural gas tank you see some places? And it was pumped in, and apparently, this is not when the explosion took place, but he said that, one time that there was a little leak in the flooring tank out there. And his PhD boss sent him out there to fix it or something. And he said he went out there and there was a bolt, and it was like just kind of orange red. It was like the bolt was hot, and, you know, and they had to fix it. But he told me something peculiar. He said that there were sort of bees flying around. And he said that actually fluorine has a faint smell that insects are attracted to. And he still remembers that the bees were flying around out there. You know. He said it's amazing that tank just didn't explode. You know.
It attracts all the insects.
What's his name?
So that was, you know, back in the archaic 1960s. Well, you could go back to 1900 or 1895 when fluorine was discovered. And there's a little something used to be on my board when they were isolating fluorine back then, 120 years ago. And it says in their own writing, some fell on the floor, and it says as soon as it hit the floor took fire. Because back then the floors were wood. Okay? I mean, chemistry. You know, things become safer and more known, and now you can control things. But guess what? There's other things that are being created in other chemicals right now that are just as dangerous because they've just been created. You know? Like SF5. Actually, it might be pretty stable, but things that are just now being used and learned about. Okay? So you bring in water, you get what type of product? Halohydrin, typically also chlorine and bromine. Sometimes you see iodine here because you can't get an iodine OH product. Occasionally you can have iodine. Peroxy acid gives epoxides. These two bonds would actually be cis. They have to be. You can't have a trans three-member ring. Cyclopropanes, these two bonds would have to be cis. They have to be. And that would have to be okay. This can help you with your stereochemistry. Or we can do chloroform hydroxide, have two chlorines on the carbene, make a dichloro cyclopropane. Gem dichloro. What is geminal? Geminal means twins, like Gemini. Two chlorines on the same carbon, they're like twins. A gem dichloro. Okay, the next reactions we'll be looking at. Look at there, we did 3/4 of them. Two more here and then one below. The next two are making alcohols. Okay? These are really ultimately hydration reactions. That is, we're adding H2O. But this is a lot more than just water. This is the ultimate outcome. Okay? It's a boron reagent. But the ultimate outcome is we're adding water. These are two unique and useful ways to hydrate an alkene other than just using acidic water. Okay? We'll look at those. Please be looking ahead because we're going to keep up a good pace. We'll be using these principles we talked about. Back bonding, mechanisms. And then we'll be moving to stereochemistry on Monday. I gave you this handout today. Have a good weekend, guys. Case study all weekend. Okay, make sure you get out and get some fresh air. All right, take a walk. Then get back at it. Do a little yard work.
Send it to Robert.